If I invert the particles, do I get what I started with? Or do I get a minus sign? And that has to do with the fact that the perturbation operator, or the permutation operator, did I talk about the permutation operator? Which is doing that. Yeah, let's do it. We talk about operators and wave functions, right? What is an operator? What does it do to a wave function? Something. That's the way to think about an operator. I can make anything I want into an operator. I can talk about the square root operator if I want to. Problem is, the square root operator is not a linear operator, and the wave functions need to be linear. They are linear, and we can't mess with them. So we mostly care about linear operators. What about this operator? What does that do?
It's a partial derivative.
Takes a derivative, right? Yeah, it's got a little curly d's and straight d's, but the main thing, we don't even need that. That says take the derivative. But what's special about it in quantum mechanics? Why is the derivative operator, the space derivative operator, special in quantum mechanics?
Does it give you kinetic energy?
Momentum. If I do it twice, it gives me the kinetic energy. So one derivative is the slope of the function, that's the momentum. Two derivatives, and that's this whole trajectories are out the window. We've lost those from the uncertainty principle. Can't talk about a trajectory. What is a trajectory? Can't. Yeah, it's where it is at every time. And I can't tell you where a particle is at every time. I can't tell you about the trajectory. Because even if I know it at one particular place, I don't know where it's going now. Because if I know its position really well, I don't know its momentum at all. And that means I don't know where it's headed. So the idea of a trajectory, a place, a record of where the particle's been at every point, gone. We can get close to it sometime. Protons very often, we can treat those as little BBs flying around. That works okay. Electrons, much harder because of that tiny, tiny low mass they have. So electrons are a much bigger problem for that. So what replaced them? The wave function. How do we get information from the wave function? We do operations. We do things to the wave function and it tells us stuff. It tells us whatever we can get from it. I mean, whatever we can know is there. If it's not there, we can't know it. That's the way to think about it. That's the way I think about it. So, many, many operators. One of those is the permutation operator. I'm going to go ahead and write it out. I think both of these textbooks use a capital P for that. That can be a little ambiguous depending on the other books that you pick up. If I say the permutation operator of psi of x2 minus x1 is psi of x1 minus x2, where I'm just relabeling particles. What happens if I do that twice? Well, that's like doing this onto this. What happens when I do that?
We get psi of x1 minus x2.
And then do that.
So it's just going to be back the way it was.
Yep. So if I do that twice, I'm back where I started from. That means the natural wanna say eigenvalues, but I don't wanna say eigenvalues. I know what we talked about energies. We talked about a particle in a box. And we'll talk about them more, and you said you have that energy, and you have that energy, and you can't have any energy in between, right?
You can.
You can. So why do people keep telling you all the time that you can't?
Because it won't stay there.
Yeah, there's something special about those particular states. Those are special states associated with the energy operator. That's the kinetic energy operator. When I do that to a wave function, I get one of these numbers. And the wave function associated with being there or being there. That's the special states associated with any operator. There are certain special states associated with every operator. They're called particular functions, particular values. Germans would say eigenvectors and eigenvalues, and because they invented a lot of this, we have to do it their way. So we call them eigenvectors and eigenvalues, eigenfunctions. So this is an eigenfunction of that operator, because when I do it twice, I get back what I started with. That means if I do it once, if I do it twice, I get 1, and that means if I do it once, I have to get +1 or -1. If I apply it once and I get the function I started, what I just figured out is that this has to be ±1 psi of x2 minus x. When I permute these, I have to get back what I started with a ±1 times it. Why? Because if I do it twice, I get a +1. There's a +1 here. I see it? There's a +1 right there. It's the only thing you can square and get a 1, a plus or minus. +1 worked, so does -1. So that's where this idea of permuting the labels becomes important, and why you wind up saying that they need to be either plus or minus whenever you apply that. When I permute them, I can get back what I started with, or the same thing with a minus sign in front of it. So that's why we care about those. Well, that's sort of the mechanics of it. We care about them because they help us bring order out of chaos. And so what I've sort of mentioned before is that we have this chaos of all these different particles. They started banging particles together. We know why they hit them harder and harder and harder, because that allows you to look closer and closer and closer. Go back to the beginning, take my electron, bang it into my proton. The faster and faster they go, the more information I get about what's going on inside there. And so you want to go to higher and higher energies to get better and better resolution about what's going on there. I know it's a certain size, and that's all I know. When they first did this, it was, okay, spherical. But it's only spherical on some scale, right? That's like something, a weird shape 100 miles away looks spherical. Stars all look spherical because they're so far away. They are, but for different reasons. They look like that because we can't resolve them. You can see the mountains on the moon if you look, if you magnify the image, but not if you look with your naked eye. Increasing the energy of these electrons gives you more and more information. But eventually you start making other particles. Some of that kinetic energy turns into other particles. Now you got all these other particles, you got to figure out what's going on. So you want to bring order out of chaos. Part of that has to do with symmetries of the wave functions. And this idea that I'm fixing to talk about of isospin, which seems made up. And that's because it is. And so you say, well, how can you just make stuff up? Because you let me get away with making up charge. And you let me get away with making up mass. And now it's too late. If I get to make those up, then I get to make everything up. It's called isospin because it's kind of like spin. Iso, I'm pretty sure comes from isomorphic to spin. It's mathematically the same as spin. And then, well, since it's kind of like spin, and spin is kind of like angular momentum, except it's spin angular momentum rather than orbital angular momentum, you could say, well, it must be some kind of angular momentum, except there doesn't seem to be any reason to believe it has anything to do with anything spinning anywhere. We're already in trouble here when we try to interpret an electron spin as a thing spinning. We run into no end of difficulty trying to calculate that. What's the velocity, and on and on and on, right? I mean, it's just, there's no way to make it work. It does seem to be related to that because mu equals we got that from angular momentum, right? Something, a charge spinning with a certain angular momentum has a magnetic dipole moment. We did that, we talked about that. Magnetic dipoles are related to the motion. Well, that makes sense. A magnetic dipole is a current around an area. So a loop of current around an area has a magnetic dipole. Protons, those are charges spinning around, so that seems to make sense. This says spin is probably some kind of angular momentum. And the reason I think this is true is because when I put these in a magnetic field, they respond. They feel a force from a magnetic field, just like Maxwell said they should. But there's a 2 missing, and it can't have any value it wants. It can only go up or down. Even if the spin is turned to the side, it will only go up or down. If I can make the spin be to the side, it changes, and it goes up or down. So there's a lot going on here that says it's kind of like angular momentum, because it's kind of not like it in other ways. This, they call it that because it has some of the similar mathematical properties, but that's the only reason. Doesn't explain any sort of magnetic effects. It's not like a current going around in a circle. So it's just kind of like spin in that there's a TZ that goes from minus t plus 1, 0, t. Because we saw that before. If your spin is 1/2, then your z component can be plus or minus 1/2. But if your spin is 1, what are the possible values for S of z? I'll give you a hint, it's a triplet state. That's going to tell you how many there are. Triplet state, how many options do you have? 3, good call. And what are they?
It's a minus 1. 0 and 1.
So 3 possibilities. And if your spin was 7, what do you bet there are? Starts at the bottom and steps up by 1. So if your spin was 3, it'd go minus 3, minus 2, 0, minus 1, 0, 1, 2, 3. So you have 2s plus 1, twice as many plus the 1 in the middle. That's where that degeneracy comes from. Isospin is going to do the same thing. Isospin is going to help us understand nitrogen, for one thing. What's weird about nitrogen? Go back to the beginning of the semester. What's weird about nitrogen? First, it's crazy stable. Now I mean chemically as well, but the nucleus is crazy stable. Why is, not really, carbon so crazy stable? The nucleus. Why is it so tightly bound?
Even?
It's even. And it's even better, it's 3 heliums, right? So it's even, and the two evens are divisible by 4, I guess. No, 6. Yeah, even is what that does. So what about nitrogen? I went off the reservation for a second, but I'm back now. You're right, even. Nitrogen. Why is it so crazy stable? Odd. Yeah, it shouldn't be. Yeah, it shouldn't. It should be ready to go. They should not want to be around. Isospin helps you sort of figure out, oh, it's a weird counterexample to everything else that we see up there, and it's this isospin helps us figure that out. Doesn't explain it, just says, oh, okay, yeah, it has this isospin configuration, and that whatever isospin is, it reflects that that's more stable. So, I'm talking about isospin. We're going to talk about wave functions that are just like that. So let's talk about, and just recap our 2 nucleon states. They can combine into certain spin states. What are they? I got 2 nucleons. They can both be spin up. They can both be spin down. One can be up and one can be down. Or I guess the other way too. That's every permutate, every combination that you can come up with. So what's wrong with those 2 nucleon? And right now I'm thinking in terms of spin states. What is the concern? If this worked, we would just do this, right? This doesn't work. This doesn't fit experiments. Because I'm implying you can do something that you can't do. And I have to pretend, at least mathematically, to fit my data, I have to pretend that one thing is not true. Hint, they're identical.
So you can't have 2 spin up or 2 spin down?
I can do that. That's okay, because I know that one of them is up and the other one's up. I know one of them's down and the other's down. What I'm saying here is I know that particle 1 is up and particle 2 is down. Here I'm saying I know which one. So what have I got to do? What I've got to say again?
You add them? Like
I have to
these 2?
create a linear combination of them. Exactly right. So now I've mathematically made that impossible.
I have a question. Okay, so last class we kind of wrote them a little different. Does it matter? Like with the, like we did like the kets and then like 1 and 2. Does it matter if you do it 1 or 2 or combining them like that?
I'm shortening that a little bit because we have all that. And if I do this, that's what I did before. That's so much work.
But it's the same thing.
Yeah,
Okay.
because now, as I go across here, you're gonna believe that that's number 1 and that's number 2. And I know one's up and the other's up, and I know one's 1 and one's 2, but I don't know which is which. This would be the same if I labeled them 2 and 1. This is probably a little more safer and more careful thing to do. I can do this faster, and that's all. And that happens a lot. early on, they'll say what their convention is, and then from then on, they'll do it that way. So this is that. Is that okay?
Yes.
So this is not different so far. What's the difference between these? Because one of the things you showed is that the spin of this is 0, whether there's a plus there or a minus there. So what difference did I say there was? And I waved my hands about this. We didn't actually show this in detail. I asked you to do the z-spin operator for 1 and 2 on that and show that you got 0. But I didn't tell you that you had to find the total angular momentum of both of those. And that's the difference. There's a plus, SZ is 0 for both of those. With the plus, S is 1, and with the minus, S is 0. So if S is 0, then SZ can't be anything except 0. If S is 1, then I've got 3 possibilities for SZ. It can point all along Z plus 1. It can point down in the minus Z direction. Or it can be horizontal and have SZ 0. So that's my triplet state. Now, talking about isospin states, this comes up in this idea that we have a nucleon. And the nucleon can be in the neutron state or the nucleon can be in the proton state, or the nucleon can, well, I've got 2 nucleons. They can either both be in the neutron state, they can both be in the proton state, or they can be one or the other. One can be a neutron, one can be a proton. These are 2 states of the same wave function. Where we're headed here, or what we're not headed here, we're just touching our toes and we're gonna walk away. This idea that fields are the only thing that's real. Who's had 222? E&M. First E&M class. You're in it right now, right? You're in it now? Yeah. So you've heard of fields. What kind of fields have you heard of?
Like electric field.
Magnetic fields.
Magnetic field.
They may have talked about the gravitational field in hindsight. They may not have talked about it in 221, but there's a gravitational field. There's also baryon fields. There's lepton fields. And so electric and magnetic fields, you have a field and then particles are a manifestation of the field. If you took any computer science classes, they talk about a process and a manifestation of a process. This is a similar idea. You have a field that's everywhere, always. And you have an excitation of that field that is a neutron. Or you can excite that field and make a proton. Or you can excite that field and make an electron. You can excite that field and make a photon, which is not a particle of light. So you have these fields and you create particles as an excitation of that field. So that's the way to think about this. I have a nucleon field, and a manifestation of that field could be a neutron, could be a proton. What's wrong with that last one?
You're distinguishing which one?
And even though a neutron and a proton are distinguishable, a nucleon is not. In the same way that this electron spin up is distinguishable from this electron spin down. The electron itself is not distinguishable. The state, 2 different states of an indistinguishable particle. 2 different states of an indistinguishable particle. Better? Happy now? Now what's wrong?
Has to be the combination.
Yeah. At this point, I'm saying that particle 1 is a neutron and particle 2 is a proton. And I have to do the same thing. I have to create a linear combination of them. Looks a lot like spin, doesn't it? It's isomorphic to spin. And this idea of T being the property that tells me about this indistinguishability. If I do, what would you say is T for this? T and TZ. T, TZ. T, TZ. So I'm asking you to use what you know about spin to tell me what must be the case for the isospin and the Z component of isospin. Remember, there's no axis, there's no Z axis, there's no Z component. It just does the same stuff and behaves mathematically the same way, so we use the same term. Over here, what is S? Is SZ.
This is 1.
Plus 1. The way I think about them is they're adding together to give me a spin of 1, and they're oriented along the Z-axis. What about this one? They're oriented together. So S is still 1. What is SZ?
Minus 1.
Minus 1. Very good. What about here? Depends whether I have a plus or a minus, right? If I have a plus, what is it? You just got to remember, because we didn't actually do this in detail. What was this case?
1 and 0.
Yeah. S is 1. SZ is 0. If I use a plus sign, if I use a minus sign, what is it?
0 and 0.
Yeah. That's no angular momentum, and so of course, no Z component of angular momentum. Same thing happens over there. So these two are isospin 1. Now I can't remember. Neutron, minus 1, 1, plus 1. With the plus sign, that's 1, 0. And with the minus sign, that's 0. And so you then go with, for nucleon, I'll write this down. So I need to double check this.
I think that's right.
Neutron. Neutron's minus a half.
Mm-hmm.
And so the nucleon state has T equals 1/2. So
Bless you.
even though you didn't really sing, you kept it in. Rest. Your soul still left your body. So let's talk about a deuteron. Which of those could possibly be a deuteron? Well, what are we used to thinking of a deuteron as?
Proton and a neutron.
Yep. But now with this new picture of the nucleon field and an indistinguishable nucleon in one of two states, proton, neutron, which of those can be a deuteron? Can this be a deuteron? Can this be a deuteron? In fact, we've given that a name. What do we call that? Two neutrons. Dineutron. Two protons. Diproton. Very good. What about a neutron and a proton? That was a deuteron. Right? But we've been thinking of it as this, but this isospin business, which I promise you is going to help us understand that neutron, that nitrogen thing, doesn't let us treat it this way. It's got to be one of these linear combinations. And the minimum energy, the lowest energy would be NP minus PN. Because that's the one with zero isospin. And the minimum isospin gives you the minimum energy. That's empirical. I don't know that there's, I don't know what the any deeper explanation for that. So if this is my isospin state, does anybody remember what the actual spin state of the deuteron is? Anybody remember what the spin of a deuteron is? Somebody who's maybe doing a project on it?
It's spin 1.
Yeah, it is spin 1, right? So that means it's one of these, or so under exchange, I permute the two particles. What symmetries do I have here? The spin state is this one or this one or that one. And which one depends on how that spin is oriented. So you can put it in a magnetic field. That deuteron spin is going to try to align with the field, or it'll be aligned against it, or perpendicular to it. But the main point is that spin 1, it's this triplet. What is the symmetry of the isospin? What is the symmetry of that? And that's going to tell us what the symmetry of the space wave function is. If I permute my particles, do I get my wave function my isospin wave function back, or do I get the minus of my isospin wave function? Or if you want to, you can work on this one first. If I'm in my triplet spin state and I swap my particles, do I get my wave function back, or do I get minus my wave function back?
Minus?
That's one of them, right?
Mm-hmm.
That's SZ plus one. If I swap my labels, if I swap my particles, do that, swap the states, swap my plus and minus, my one state and my two state. What happens to my wave function?
It's the same.
Yeah, if they're both up, go through there, make sure you convince yourself that that gives you the same function, and that gives you the same function with a plus sign. And we did that one with the spin operator. We kind of dove into that one. And I had you do it for the minus sign. I think I charged you with that. Any one of these is even. The deuteron spin is even when I permute those up particles. What about my isospin? If I'm in this nucleon state, do I get my wave function back, or do I get minus my wave function back? Somebody probably said something. Minus. I get minus, it's odd, under exchange, different ways to say it. So, if my isospin function times my regular old spin function, is that even or odd under exchange of particles?
Odd.
Odd, because the spin is even, so nothing changes that. That one's odd, and so they're odd over together. So my wave function is going to be an isospin part times a spin part times a space part. Tell me about the symmetry of my space part. Hint fermions.
Is it odd?
Well, if it were odd, I would have even times odd times odd. I'd pick up a plus sign and a minus sign and a minus sign. What would my overall wave function be? Plus one times minus one.
Plus one.
Be positive, right? Be an even under particle exchange. These are fermions.
So,
Yeah, that would be really, really weird. If you could prove that, come tell me. Only me. But in fact, it doesn't fit with anything else that we've done, any of the other experiments that people have done. Everything holds together as long as you have an odd function. So what does that tell me about my space wave function? Odd, even. That's how I get an overall odd wave function. So my space wave function has to be even. And if this is x2 minus x1, to be even, that's the kind of function we wrote before. An even function with symmetric on both sides. If I plot it against the different distance between the particles. that means they have a tendency to stay closer together. They can be far apart, but the probability is that they're closer together than if they were in an odd function. It's our odd function where there was not much probability of them being close together, right? They tended to stay far apart from each other. So now let's think our way through one of these. What changes? Can you tell me about the symmetry of any one of these?
It's
With
even.
the plus sign. Yeah, that becomes even now. And that's, if that's still even, my space function has to be odd. That pushes them apart. If they're not close together, they don't quite bond. The exclusion principle, the Pauli exclusion principle that says you can't be in the same state, which is where all this comes from, the symmetry of wave functions says that the particles would tend to stay apart. And if they're too far apart, because this is such an incredibly short-range force, they can't bond. So I don't have T1, Tz equals 0 dineutron. I don't have the plus version of that. The plus version of the deuteron. I only have the minus version of the deuteron. What's the one hole in the argument? If my spin is even and my space is odd, then my isospin has to be even. But notice I got three functions, right? Why can't my isospin be even, my space be even, and then my spin's odd? Because then I'd just be in this state, right? And a priori, there doesn't seem to be any reason to. I don't know of any overall reason, except that there must be something about the strong nuclear force that it has an angular momentum dependence. We know that because we had that S dot L term. I'll come back to that in a second. We know that there's something about the nuclear force that has to do with angular momentum. The force depends on angular momentum, not just distance between them. Like the Coulomb force only depends on how far apart you are. The Biot-Savart law for magnetic forces only depends on how far apart you are. But there was this S dot L term when we were trying to calculate the states of the particle in a box states. We were able to explain that table as long as we included an angular momentum dependent term in the Coulomb force, in the nuclear force. So apparently that force prevents that from happening. Prevents me from being close enough together to bond if I'm two protons or two neutrons. The symmetry, this stays an even spin state. Spin 1. And the proof, quote unquote, of that is that nobody's ever seen a diproton. Nobody's ever seen a dineutron. So that is isospin. If you go through and look at all the nuclei, and he does examples in the book. I'm going to erase them. I guess this one over here. Empirically, the ground state is lowest possible T. So So for a deuteron, TZ equals 0. And that's in both cases, right? Both linear combinations are TZ equals 0. And so if you know that TZ is 0, what is the lowest possible T? All you know is TZ is 0.
Zero.
Could be 1, right? But that's not the lowest possible. T equals 0 is the lowest. So that's the ground state of the deuteron. You have these excited states, T equal 1. You can excite a deuteron into this higher state, but it's higher energy. Deuteron's barely bound already. So you give it any energy at all, they come apart. So there is an excited state, T equal 1. You have these as excited states, but because they have so much energy, they're not bound. They just take off. He shows on figure 1715, that's where your nitrogen thing happens. See what's going on with the nitrogen? Those are all A equals 14. So, was that carbon 14? Should be one of them. Yeah. And if you add all up, add up the Z, take Z minus N, you get over 2, you get minus 1 for that one. And so the ground state is T equal 1 for carbon 14. And what about nitrogen? What's TZ? Look at equation 17.4 for nitrogen. Calculate TZ.
Just be 0.
Would be 0, right? Z minus N. 7 minus 7 is 0. So what's the ground state of nitrogen?
T equals 0.
T equals 0, because that's the lowest possible T you can have if you know TZ is 0. It's got excited states. There's a T equal 1, T equal 2, T equal 3. But those are not the ground states. And the ground state is low, right? It's the lowest, A equal 14. So having a really, really low energy means you're really, really stable. So this idea of isospin at least rationalizes that. It doesn't explain it in the way that I sort of understand why that fell, but if I think about that too hard, I really don't know why it fell either. So how does it know? How does it know which way to fall? Which brings us to pions. True story. Why this knows to go down brings us to pions, which is the next step. So if you go to page something, figure 17.6, so page 623. You've got this picture, which is subtly wrong. But you have a neutron scattering off a proton. And that's reasonably easy to understand. What's really hard to understand is this scattering event. And the reason has to do with the range of the force, the energy of these particles, and how much momentum you can change. So momentum change is F delta T. Delta T can't be any faster than delta X over C. All I've done is said that if an influence propagates in time delta T, then it can't be any bigger than delta X over C, that time interval. And that says you're propagating, you're sending a signal over this distance X at the speed of light. And it can only be less than that, right? So this time can only be longer, so that's as good as it gets. That's as short as that can possibly be. So this is the work or energy. And so if I know those particles and I know what their energy is, it turns out that momentum change is way too big for the range of force that I'm talking about, which is a strong nuclear force. How do you know it's a strong nuclear force? Tell me any clue you have that it's not. For example, let me think, the electrical force.
Because it's a neutron and a proton.
Yeah, right. There's only one of them's charged. It's the only way that protons and neutrons interact with each other. Strong nuclear forces. So that's the only game in town for them. And so I know that's really, really short range, like a couple of Fermis. And we know that because of the size of those particles and the energy it takes to get them loose, and all of that stuff we did at the beginning of the semester. So I know it's a really short range. I know this number. I know the speed of light. I can work out what momentum change is possible, and this is too much momentum change. That's going this way, turning all the way around, coming all the way back. That's about as big a momentum change as you can have. So, what's the interpretation of that? Look at the same picture. Oh, they didn't show you in that picture. Oh yeah, they do. It's there. You see this experiment, right? They see the proton scattering a little bit. That's on the left side of the figure 17.5 above. Look on figure 17.5 above. See some scattering at small angles. That's this. Right? Proton scatters, but not that much. They show some scattering at really high angles. Look at the picture, and how do they interpret that? Since it can't be a momentum transfer to make that proton turn all the way around 180 degrees and go back where it came from, what does it have to do? They show it.
Switch from a neutron to a proton.
Yep. Which would be crazy, except we already know that happens. We just need them to both switch at the same time. So the pion is an explanation, an attempt to model what's going on inside there. Pion is how do we get them? What do they exchange to make that happen? Well, what's one thing they have to exchange? Okay, this could be a weak interaction. So it could be a beta particle, right? You could swap, you create and destroy an electron. That turns out to be even shorter range. We're gonna calculate that range, and that range is even shorter than what we're seeing here. This has a range of 2 femtometers or so. That's like 10,000 times less than that. So the chances of that happening essentially 0. But they do have to exchange some charge, don't they? Which is where you were headed with that, right? I assume. We know that protons change into neutrons, but we also know they only do it right here. They don't do it within 2 fermis of each other. This proton right here has got to change. So they've got to swap some charge. So I can either send plus charge that way, or a minus charge that way. That would work, right? Proton plus that negative charge becomes neutral. Neutral with a plus charge becomes that way. Or neutral that gives up a minus charge becomes positive. Or what's the other way? Proton can give up the positive charge, or it can accept the negative charge. But if I'm going to explain this with the exchange of this new particle that I'm making up called a pion, if that's what's making them interact with each other, well, what's got to be going on up there? If I'm going to make up a consistent story about this, a consistent theory of the way this works, then I've got to exchange a particle here, except here it's neutral. Because something else, here you were focused on the charge changing, proton becoming a neutron, neutron becoming a proton. But there's also something else that changes when I go from there to there. Spin 1/2, spin 1/2, no, that's okay. Spin 1/2, no, that's all right. Baryon, no, that's okay. Anything else change that we've just talked about moments ago? Something that's a lot like spin?
Isospin?
Yeah, isospin. Does isospin change there? Remind me what the isospin of this nucleon state, and how does it compare with the isospin of this nucleon state? They're both T1/2. But one's isospin up and one's isospin down.
Proton is plus 1/2.
Plus 1/2.
Neutron is minus 1/2.
So what does this pion have?
Spin.
Gotta have an isospin,
One.
right? Doesn't need a spin because spin's conserved all the way through there. But it needs an isospin. And it needs to have an isospin 1. Because it's either gotta take away 1, give me a minus 1/2, or take me from 1/2 down to minus 1/2, either way. It's gotta swap the isospin. So over here I've got minus 1/2 going to plus 1. But what about here?
It's no change.
No change, so it must be isospin 0. So let's see if we can figure out, what symbol do you want to use for a pion?
Pi.
Yeah, what a great choice. It's because that everybody else did. What do you want to call the pion that has a plus 1 charge?
Pi plus.
Yeah, what a good choice. Some of it kind of makes sense, a little bit. We've also got this neutral one. Tell me what TZ is for each one of those. Look at the picture, tell me what TZ of those has to be. Somebody want to call dibs on the pi 0?
0.
Good choice. He did his part.
That's the plus 1.
Look at the picture and tell me if that makes sense.
that be -1? Since if the proton picks up, or if it gives up a positive, then it's going to a neutron, which is TZ equals -1/2?
So here's what I think you're telling me. If I'm wrong, you tell me. But I think you're telling me that the neutron starts off TZ -1/2. If a pion, a pi plus particle goes that way, it's adding +1, -1 plus 1 becomes -1/2, +1 becomes +1/2. If I have -1 minus a -1, what do I get?
It ends up adding to +1/2.
-1/2 minus, I don't know what I said. I should have said -1/2 minus a -1. You're taking away t of -1. And what do you have left?
+1/2.
So see if both of those, make sure you could argue that both of those work for this arc as well. So you've essentially got 4 possible reactions. You've got a neutral pion that can go back or forth. Does that work up here? TZ is -1/2, goes to -1/2. So what is the change in TZ? 0. So this isospin helps us sort of figure out what the possibilities are. 4 different reactions, and you would have to consider all 4 of those if you're trying to fit this data. Okay, so where does it even come from? The kinetic energy, this starts to happen when the kinetic energy is about 100 mega electron volts. So are these nucleons relativistic or not? How can you tell whether you have to worry about relativity or not? There's a hint. Kinetic energy is 100 MeVs. Kinetic energy is E naught. Better remember what E naught is for a nucleon.
It's like 1 GeV.
Exactly right. This is around 1 giga electron volt. So 100 MeV proton isn't particularly relativistic. The kinetic energy is much, much less than the rest energy. So it's not particularly relativistic. If you had 100 MeV electron, would it be relativistic? Boy, yeah, I saw your eyes widen, absolutely. Their mass is 1/2 an MeV. So that would be 200 times. In fact, they would be going at the speed of light, right? They almost don't have a rest energy. That's where all their energy is, because this part is only 1/2 an MeV. But for a proton, this is 1 giga electron volts. It means the 100 MeVs is a small fraction. So, V, I can figure out how fast they go. I don't have to worry about all that beta and gamma stuff, right? All that beta gamma stuff we did one day. Anything wrong with that?
Units?
Yeah. What did I screw up? Look carefully. Kinetic energy really is 0.1 GeV, so that's okay, right?
Mm-hmm.
The mass really is, okay, 938. 1 GeV is close enough for us. Is the mass 1
energy in
GeV?
joules?
Say again?
You need to get the energy in joules, right?
I don't
And the
have
mass
to,
in
I'm
kilograms?
not gonna do that, because I don't wanna give up this nice unit system. I don't wanna give up the fact that those cancel. That is definitely worth using these units rather than converting everything to joules and kilograms and then coming back.
The
But I have left something out.
mass is GeV over c squared.
Perfect. This is really GeV per c squared. What happens with that 1 over c squared? It comes up as a c, right?
Mhm.
So what is this? This is really just 0.44 times c. In the business, that's called letting c equal 1, which I hate. But they do it. It's very routine. It's the first thing they do. C equals 1, a lot of stuff equals 1. And that means you gotta keep in mind, some things it's not so bad, right? If they tell you a speed in the units that c equals 1, and they tell you the speed is 0.44, you know that that's 0.4 times the speed of light. And you can see how that happens, right? Where c squared comes up on top as a c, 0.44 times c. So this is that c equals 1 unit convention. Very common, get used to it. I don't like it, but nobody listens to me. I calculated that gamma was 1.1, so not terribly relativistic, but we're not, you know, if we were looking for 3 significant figures of error accuracy, we would have to go back and do this relativistic. It's not relativistic, but it's not crazy unrelative, like we are, right? On the Earth going 40 kilometers a second, no big deal. All right, range of the force. 2 femtometers. The time is delta x over v, which is of the order of 10 to the minus 23 seconds. So what I've calculated is for 10 to the minus 23 seconds, these 2 particles are within 2 femtometers of each other. They're within range of the force. That's how long, as they go past each other, they are within strong nuclear force range of each other. Then I use the time energy uncertainty principle. You've normally seen that as delta E times delta T. In the same way that P and X are related to each other, P is like momentum comes from taking a derivative with respect to X. Energy is associated with taking derivatives with respect to time. So energy and time are sort of naturally paired. Px and X, Py and Y, Pz and Z. Energy and time are related to one another. So when I plug those numbers in, I get 10 to the minus 11 joules, which is about 100 mega electron volts. So what did we just figure out? We figured out that in the time that these particles are within this range, there's an uncertainty associated with any measurement of about 100 MeVs. That is exactly the mass of a pion. So the idea is, during that really short period of time, when they're within that range of each other, you can make a pion for free. Over this short interval of time, I don't know what the energy is to within 100 MeVs, but that's enough to make a pion. So they can make one of these pions, exchange it, and when this pion moves from there to there, there's an exchange of momentum. They exchange momentum when they go from one to the other. How much momentum? Figure that out. When I create a pion here and then absorb it there, what is the change in momentum? What is the scattering angle? If you have a proton coming in this direction and you change its momentum by what you get from a pion going there, how far does it bend? And you find out the angle, I hope, you find out that the angle isn't close to 180 degrees. These pions can't make you go that way. They have to exchange the isospin and the charge and whatever other properties you need in order to make that particle come out the other side, looking the way it does. You get to make fun of me because I'm going to start talking about Feynman diagrams.